Let's talk now about the neurologic side of things. What's happening in the brain? The brain is a beautiful, complex, difficult organ. It's not like the other organs. The brain does not work linearly like we see with the kidneys and the pancreas and the thyroid gland and the liver, right? It doesn't work linearly, meaning it produces something, it secretes something, it responds to something, and on and on and on it goes. No, the brain is unique. This understanding that it's not a linear organ, it's not a computer like we thought it was before, but that it can change, it can alter, it's dynamic. Our understanding of that has led to more discoveries neurologically than before. It's beautiful the way it works, but it's incredibly complex. We think we understand something, and then more research into it, and we realize, we really didn't understand this at all. We think we understand that by giving an SSRI, a selective serotonin reuptake inhibitor, to a person suffering from anxiety, we think that by giving that it's increasing the amount of serotonin, another neurotransmitter, in the brain, which helps the anxious person. But now we realize that SSRIs might not do so much for our serotonin, but might have more of an effect on decreasing the dopamine on the other side. Anyways, it's very, very complex, and so our understanding is growing more and more and more as we understand more about the dynamic nature of the brain, and that's something. So, as far as the brain is concerned, we have to consider something called neurologic regulation. How does the brain work basically? Well, the brain uses chemicals, but it also uses electricity, electrical activity. And we can measure that by using something called an EEG, an electroencephalogram. And what we look with an EEG is the brain wave activity. What kind of electricity is there? How much is there? What types of waves? What's the frequency of the waves? How many wavelengths are we seeing in a certain amount of time? And then, is that appropriate or not? You can see on the screen here, I've got 4 of these wavelengths listed: delta, theta, alpha, and beta. And those are the 4 best known wavelengths. There are others, there's gamma, and and on and on it can go. But these are the best known, the most commonly known, and these are the best researched. Reason being is that muscle movement in the body, right? When I blink, when I move my head, when I move my jaw to speak, when I and those kind of things, those affect the electricity in the brain. But delta, theta, alpha, and beta are the ones least affected by muscle movement. The ones beyond that, they're so affected that it becomes difficult to really measure them with any sort of accuracy. And so these are the 4 main ones. Anyway, delta wavelength. We see delta the highest during deep sleep. That's when delta is supposed to be most active. We see it most active when, during deep sleep and when we're when growth hormone is at its largest. Theta is your twilight wavelength, when you're drifting off to sleep. It's associated with creativity. That's why you have your best ideas just as you're drifting off to sleep. And you always think to yourself, well, I'll remember that in the morning. How could I forget this great idea I've just had? And then you wake up and it's like, oh, what was that again? I don't remember at all. That's theta. Alpha, you're awake, but you're meditative. You're quietly restful. You're calm. That's alpha. And then beta, you're awake, you're active, you're alert, you're doing, you're being. That's beta. A lot of times, nowadays we have the ability to look at these wavelengths and to compare them to normals. And so we know how much we should see of delta during a certain time. We know how much of theta we should see, and alpha and beta, and same, those kind of things. We have normal ranges for those now. And so we have the ability to run this scan, this brain scan, to look at these wavelengths and to understand if something's wrong or not. For example, with anxiety, we see excessive amounts of beta wavelengths. Excessive amounts of beta lead to these symptoms that you can see here below. Your brain is stuck in a fast processing state. It doesn't have the ability to really transition to the idle processing. It can't transition from fast processing to idle processing, which is your alpha, or from idle processing to slow processing, which is your delta and your thetas. And so when it's stuck with this overactive beta, we see anxiety symptoms. We see panic attacks and worry. We see hypervigilance and insomnia, like we talked about before, obsessive thinking, poor emotional self-awareness, and those kind of things. The brain can't transition to idle and slow processing and then from slow to idle to fast processing. That's typical of what creates an anxiety picture in these kids. Now, I mentioned my son before, Ethan. And in him, where we were seeing symptoms of ADHD, we expected to see his brain to have overactive theta activity, which means he would have been stuck in slow processing with the inability to transition from slow to idle to fast. That's hallmark, that's classic for ADHD. But when we ran his scan and we looked at him, we saw that beta was the issue. I realized that ADHD wasn't the problem at all, it was anxiety. And so as we started treating him for beta issues rather than theta issues, then he started responding. Then we started to see the difference, the huge difference in him right away. I want to show you real quick a before and after scan of one of my patients. This is the before scan. I'm going to show you this patient later on. This is the before scan, and I want you to look. We've got two different areas we look at here. There's more, but I've included two here that we're looking. There's the delta, theta, alpha, beta from left to right that you can see there. And we're looking at magnitude of the wavelength. How tall is the wavelength? And then we're looking at the asymmetry. Is it higher on the left or is it higher on the right? And those kind of things. With magnitude, now there's a lot to look at here. There's low delta, low theta, but the big thing I want you to see is high beta in the posterior of the brain, the back of the brain. That's indicated by the P3, P4, O1, O2, and the T4 on this patient. On top of that, I want you to look at beta in the asymmetry. Now, beta for asymmetry should be all blue on the right brain. It should be all red on the left brain. Alpha is supposed to be just the opposite of that. So you can see alpha is pretty normal there. Beta should be that C4 spot. It's the high beta at C4 and the high magnitude of beta at P3, P4, O1, O2 is what was causing this patient's anxiety. And again, I'm going to show you him just a little bit later on and tell you about what he experienced. But we worked with him for a little while, and here's the after scan. There we go. Look what happened to P3, P4, and T4 on the magnitude for beta. It's normalized completely. Look what happened to that C4 asymmetry that we had at beta. It normalized. And so guess what we saw in this patient? We saw the reduction of the symptoms associated with high beta magnitude and beta asymmetry, which includes anxiety, which he experienced, panic attacks, which he experienced, huge panic attacks, to the point of hospitalization again, because we normalized these wavelengths. So that's one way of looking at the brain, understanding how the brain regulates itself. And we have the technology now to do this, which is amazing.